In this video, we'll be taking a look at a problem involving Coulomb's law with charged shells of uniform charge density. Typically, when we have charge densities as opposed to point charges, we have to do some sort of integration either over a line or a surface or a volume of some sort. However, in this problem, we'll see that we can use a shell theorem to avoid having to do the integration and hopefully solve it a little more quickly. Let's go and take a look at the problem statement. Okay, so in this problem we have an electron inside of a charged shell, and we know the initial speed of the electron. We also know the characteristics of the shell, such as its charge density and its radius. What we're asked to find is what is the speed of the electron once it's a distance of 2r outside of the shell. So the question says to find the velocity when the radius of the electron is 2 times the radius of the shell. Now, because this is a charged particle and it's in the presence of other charges, it's of course going to feel a force given by Coulomb's law. And that force will cause an acceleration due to Newton's second law. And then once we have the acceleration, we can find the velocity just using kinematics. So the approach here will be to find, first let's find the force using Coulomb's law. So that'll require knowledge of all the charges, their distances from this charge. And then from that we can find the net force upon that particle at different distances from the center. So the force is a function of r. Once we have the force, of course, we can just simply use Newton's second law to find the acceleration, F equals ma. And then, as is always the case in mechanics problems, once you have the acceleration, you can find any other kinematical quantities such as velocities, distances, and times. In this case, we're going to look for the velocity, so we're going to integrate the acceleration along the path to find the velocity at r equals 2r. Okay, so let's go ahead and carry this out. The first step will be to find the force when the electron is within the shell and outside the shell. So I want you guys to go ahead and do this on your own. Find the force when the electron is inside of r, and then when the force when it's outside of big R. And what you want to do is get an expression for the force in terms of its radius, in other words, its distance from the center, along with the charge density of the shell and the radius of the shell, and any other constants you may need to use. Try to get an expression for that. You can have two distinct expressions, one for inside and one for outside. Try that on your own. We'll come back and take a look. So now normally when you have a charge density, you'd have to integrate the Coulomb's law over the entire charge density, and that would require the use not only of integrals over various dimensions, it would also require the use of vectors. You'd have to decompose it into different vectors in different components and then add up all the vectors at the end. So it's quite technical. In this case, we have at our disposal the shell theorems. And the shell theorems say that when you have, and as we do here, a uniform charge density on a sphere, then the force actually reduces to something very simple, both inside and outside of the sphere. When you're inside of a sphere of uniform charge density, so keep in mind it has to be uniform charge density and has to be spherical. When that's the case, the force inside is actually 0. So all those forces added up from every single portion of the shell cancel out to be 0. So that's actually very simple. And then on the outside, it's also something quite as simple. When you're outside, you can treat the entire sphere of charge as if it was a single point charge at the very center, whose charge is equal to the total charge on the shell. And so we can treat this as if we had, instead of a charged shell, we just had a single point charge at the center. And the point charge, by Coulomb's law, the point charge gives a force of the Coulomb constant times the product of the charges. So in this case, the charge of the electron is E, and the charge of the entire shell I'm just going to call Q shell, divided by the radius squared. And so for Q shell, that's going to be the total charge upon the shell. Now we have a charge density here, so what I'm going to do is rewrite that that total charge in the shell as charge per area times area. And this charge per area we have, which is sigma, and the area of the shell is 4 pi r squared. So the area of a sphere, the surface area of a sphere is 4 pi r squared. And you want to use big R here because we're looking at the sphere, not where the electron is. So it's 4 pi times big R squared. And we have sigma and we have r, so we could actually evaluate this Q numerically. And so what we have here is we have an expression for the force inside the charged shell and outside the charged shell. Inside is quite simple, and outside is also it's not too hard. Now the next part is to find the acceleration, which we can find using Newton's second law. So Newton's second law says that the sum of the forces equals the mass times the acceleration. In this case, we only have one force given by Coulomb's law, so using F equals ma, we just divide by m on both sides to get that the acceleration equals the force divided by the mass. Inside the charged shell, of course, the acceleration is 0 still, and then outside, the acceleration is this quantity divided by the mass. So let me go ahead and write that in terms of Q shell, which is this quantity right here. And then you're still dividing by r squared. We're going to divide by mr squared to find the acceleration. So this is the acceleration outside of the charged shell. Now that we have an expression for the acceleration, the last part of the problem is to integrate this over a distance to find the velocity at the very end. We may be more familiar with the fact that to find a velocity, we integrate acceleration over time, but we don't have acceleration here as a function of time, we have it as a function of distance. So the relevant formula here that may be a little less familiar than the one that we're typically using with accelerations to get velocities is this formula, which says that the difference of the squares of the velocities equals 2 times the integral of the acceleration over the distance squared. All right, so here we have an acceleration. We know we're integrating it from the very center where the electron starts to 2 times the radius outside where it ends. So we're going to integrate this from 0 to 2r. And we have to do it in 2 pieces. The first piece will be from 0 to r because we have a particular expression for acceleration there. And then the second piece will be from r to 2r because we have a different expression for the acceleration outside there. Go ahead and carry this out on your own and try to find an actual expression for the velocity. And you can plug in the numbers to find the actual numerical value for the velocity when the electron is at 2r. Go ahead and take a minute and do that now. We'll come back and take a look. All right, so for the velocity outside of the final velocity, we're going to have that the vf squared equals the initial velocity squared, and I'm going to break up this integral into 2 different parts. One for inside of the shell, and I'm going to integrate the acceleration formula that's relevant inside there. So let me just call that a in, which is this formula right here. And then the second part, I'm going to integrate from r to 2r, and I'm going to use the acceleration formula that's relevant there, which I'm going to call a out. Now plugging in each of these formulas one by one, this obviously just gives 0 because I'm integrating 0. And then the second part, I'm going to have 2 times this guy integrated. Everything here is a constant except for the 1 over r squared portion right here. So I'm going to have 2 times that guy. So 2 times ke times e sigma 4 pi r squared. And then the m is also a constant. And you're going to be integrating 1 over r squared. The integral of 1 over r squared is minus 1 over r. So you're just going to have minus 1 over r evaluated from r to big R to 2 times big R. All right, so plugging all that in and then using the values given, we know the initial velocity, we know the mass of the electron. You can look up, you can just look it up online, and then we also have the constants, the electron charge, sigma is given, and big R is given. So plugging all that in, you should find eventually that the final velocity is 1.74 times 10 to the 6 meters per second. All right, so it's going about 1 million meters per second. Now in this problem, we had to use a little bit of calculus to find this, but ultimately we were able to bypass a lot of the complications involved in finding forces upon charged particles when you have uniform or any sort of charge density because we were able to apply a shell theorem. So the useful trick here was that we recognized that we had a spherical situation here and it had a uniform charge density, so inside the force was 0 and outside the force was as if this is just a single particle at the center. So being able to recognize this is very useful because you can avoid doing a lot of unnecessary calculus and integrals. So let's go ahead and take a look and summarize what we've done here. In this problem, we were asked to find the final velocity of an electron as it accelerated through a charged shell. First, we applied the shell theorem to determine that the electron underwent a net force only when it was outside the shell. Then we used the force to find an expression for the acceleration as a function of radial distance. And finally, we integrated the acceleration along the path to find the change in velocity. All right, so that's it for this problem. If you have any comments or questions, please leave them on the link attached to the video, and we'll see you next time.